This video we're going to talk about 2-3 trees. So this is just one other tree it's nice to highlight and chat about to see another version of a balanced search tree. So this is called a 2-3 tree, which a 2-3 tree is a B tree. A B tree could have, any number of nodes coming off of it, and so it's a B tree with M3, and also known as a 2-3 tree. I just feel like I said a lot of numbers that didn't make very much sense, but this could be called a B tree with M equals 3 or a 2-3 tree. So it's another balanced search tree, but you'll notice that instead of having, binary 2 nodes each time, it has more. Nodes store 1 or 2 keys, and so you have a much wider tree, and so the height is not as tall, so it's less steep. Each node has 2 nodes or 3 nodes, denoting the number of children. And it has strict balancing, so all the leaves have the same number of depth, so you fill by level, and so it really widens out the tree. There's no rotations, instead you split the nodes and push the values up as you insert. It's definitely more complicated to program, especially generally for any number of nodes. And so here, if you just want to kind of observe what this looks like generally, you can see that you start off here with 15 and 26, and then you branch off into 3 different places, and each of these nodes either has 1 or 2 values. And when you branch off, you have something that is in between the 2 values. You have values that are greater than 26, and then you have values that are less than 15. And then you basically have that same thing in every case. So here you have a value that splits between 5 and 9, a value that's greater than 5, and a value that's greater than 9. And then here you have just 2 because there was no value here, and so you have 18, which is less than 21, and 24 and 25, which are greater than 21, but they're also less than 26. So you can kind of see how it's sorted. This is a definitely more complicated algorithm to understand with, in just a few minutes. We're not going to go into red-black trees or 2-3 trees in depth, to understand the details of the algorithm, but just to get a sense of how the tree looks. So one really useful tool to kind of see what it looks like is to use this visualization, which showed a couple different times. You can use this for the AVL trees, the binary search trees, red-black trees, or B trees. So this is a B tree with max degree 3, so that's M3. So I'm just going to start inserting nodes in, and you can kind of see how it builds it. So it starts off with 100. And now we insert 50. So 50 goes on the left of 100. And then we insert 120. And so then it splits. 50 is the root node, or 100 is the root node, and then 50 and 120 go off of it. And then 80 gets inserted. And so 80 becomes part of the 2 node there. And then 60. So you can see that filled that 2 node, and once it got filled, it actually pushed it back up into the node above. And then we will add 75. So 75 joined 80 into a 2 node. Then we'll add 76. So what happens when we put it in between? You can see that it pushes it up, and then those actually have to split, and then now we have 3 levels. And so what it does is it fully fills the tree levels, so you never have extra nodes at the bottom as leaves that cause imbalance, so it stays really well balanced because it tries to insert at the top level first, and then it just keeps trying until it finds a place, and then it pushes up and rearranges. So that is a little bit about a 2-3 tree or a B tree with M3. So you can kind of see what that looks like when you're building it. To summarize a little bit about some of the trees that we've learned, red-black trees are commonly used in some typical libraries that are already set up in Java and C++ for a lot of different abstractions where data sets are typically smaller, and so it's more important that the build time is quick rather than the search time. Because people are using them and kind of like putting them into memory and putting stuff into them often, rather than more of like a permanent database, which is like set up and then just constantly being searched. 2-3 trees are commonly used in databases, in the case I just described, where you're searching a lot, and so it's cases where the data is a little bit more permanent. Maybe it's not changing as much, and you're doing a lot of lookup because the search is a little bit quicker because you are spreading the tree out, and so the depth is shorter. Then an AVL tree is more balanced than the red-black tree as well. So an AVL tree as an alternate might be used more if search is more important than a red-black tree, which has a little bit faster build time. I think that's all I wanted to say. So you kind of got a really thorough taste of AVL trees and how they stay balanced and how that algorithm works. We obviously can't spend time going through to that level of detail on every type of tree, but hopefully getting a taste of red-black trees and 2-3 trees can just show you that there's other trees out there that work very differently. Like the algorithms are completely unrelated. There's really nothing similar about them, to kind of just get you a little bit of a sense of how some of these other cases work. All right, and that's it.